before we do this lesson, I want to make sure that you have done this warm-up above. And if you haven't done it just yet, I encourage you to pause the video right now and work through these warm-up problems because I think it's a good review for geometric series and intervals of convergence, which is going to lead into what we're discussing today. And the reason why geometric series are so important to today's lesson is that it gives us an intuition for our next test, which is the ratio test, and how this particular test works. So first off, let's make sure we understand what is the ratio between consecutive terms. It's simply the value that we get when we divide the next term by the quote unquote current term. And now every series has a ratio, or we always are going to have a ratio between consecutive terms. But what made a geometric series unique was that that ratio was the same for every subsequent term in the series. No matter which terms we divided, as long as we divided the next term by the current term, we always get the same value. That's what we call a common ratio, right? So it's the ratio when the ratio between successive terms, between successive terms is equal, right? So we would say something like a sub n plus 1. This is how we would just write this algebraically, divided by a sub n. So the next term divided by our current term is some common ratio r. We know that. That's something that we've discussed time and time again when we looked at geometric series. Now, what we cared about was that the absolute value of our common ratio, whether or not it's less than 1. We know that when in a geometric series, when our common ratio is less than 1, then we know that that particular geometric series converges. So what we're going to do is we're going to use that logic and that thought process to give us an intuition for what happens for non-geometric series. And what we hope to see is that even with non-geometric series, if we have a ratio that behaves similarly as n gets very, very large, that is to say that if our ratio is getting smaller and smaller and smaller as n increases towards infinity, then it would also make sense that for that series, since the ratio is getting smaller between terms, that this series should also converge to a finite value. So I think a great problem to look at to introduce ourselves to this is to start with a problem like something like the series defined by n to the 20th power over n factorial. So let's just pause and just think a little bit about what's happening here with this series. Now, although we can start to kind of get an intuition for what might be happening by maybe using the nth term test and seeing that this series does not diverge, we want to be able to start looking at whether or not this series actually converges. So since we're talking about the ratio, let's actually look at the ratio between the next term and the current term, and let's write that algebraically. So if we're looking at the next term, we're looking at the n plus 1 order term. So I'm going to rewrite this ratio as n plus 1 to the 20th power over n plus 1 factorial. So this is our quote unquote next term, right? We're looking at our next term right now. And we're going to divide this now by our current term, which is n to the 20th over n factorial, right? This is our current term. And I'm going to rewrite this in a second, but just so we understand, we're looking at the ratio between the next term and the current term. And again, we're doing this because we're trying to see if we can get an intuition for what is happening with this series by also looking at the ratio between terms. So there's our next term divided by current term. Now we know that when we're dividing by a fraction, it's equivalent to multiplying by the reciprocal of the denominator. So I'm going to rewrite that. I'm going to say this as the following. We're going to say that this would be equivalent to n plus 1, again, to the 20th power over n plus 1 factorial. And we're going to actually now multiply this by n factorial over n to the 20th power. Now, there's a little bit of simplifying that we can do here because we know that n plus 1 factorial, this is equivalent to n plus 1. Let me rewrite that a little neater. Let's say that n plus 1 times n factorial, right? That's how factorial works. We're multiplying by all the subsequent previous terms, I should say. So we see here that we can divide out that n factorial with this n factorial down here in the denominator. So what would be all that's left over is just n plus 1. So I'm going to clean that up. So we're just going to write n plus 1 here. Okay. Next up, we see that we have, we can just go ahead and rewrite this then as the following. We can say that this is n plus 1. Actually, let's go back to blue. We have n plus 1 to the 20th power over, well, actually, before I continue, I also notice that this n plus 1 in the denominator here can divide into this n plus 1 to the 20th power up here, leaving an n plus 1 to the 19th power. So I'm going to rewrite that. I'm going to say this as n plus 1 to the 19th power over n to the 20th. Okay. Now, before I proceed, I want to just make sure that we're clear as to what we're thinking about or what our thought process should be. We're saying, we're trying to apply the same logic that we looked at with geometric series, which is if the ratio between terms is less than 1, then we know that the series converges. And that makes sense because we're saying that the terms are getting smaller and smaller and smaller. Now, for us here, we want to then look at the limit. We want to then look at the limit of this ratio. The limit as n approaches infinity of n plus 1 to the 19th power over n to the 20th. Now, I know what you might be thinking. We should say, all right, well, hold on. Our n value, this is going to depend, our ratio is going to depend on what our n value is, right? So depending on where n is, we're going to have a different ratio. So we can actually even think of this a little bit like a function. It's a function of n. Well, what is happening now as n starts to approach infinity? Well, as n approaches infinity, n plus 1, that difference between n plus 1 and n will become virtually negligible, right? And we see that the denominator has a higher degree, so that is going to be growing more rapidly than the numerator. So the limit of this is equal to 0, right? What does this mean? It means as n gets really large, the ratio between the consecutive terms gets smaller and smaller and smaller. So we can draw a similar conclusion to that of GST, right? As n approaches infinity, the ratio gets smaller. And we can draw a similar conclusion that we do with the geometric series test. And this thought process leads us to be able to define what's known as the ratio test. And the ratio test says the following. If you look at the limit of the ratio between subsequent terms, and actually I'm missing something here that just might make this a little bit cleaner. It's just to look at the absolute value of that ratio. It's a similar thought process as the geometric series test. And this allows us to work with non-geometric series. To say if the limit as n approaches infinity of the ratio between the subsequent term and the current term is less than 1, again, if the ratio then is getting smaller, that means the series will converge. If the limit of the ratio as n approaches infinity is greater than 1, or oftentimes we'll see is equal to infinity, then we know that the series will diverge. And finally, if that ratio is exactly 1, or the limit of that ratio is exactly 1 as n approaches infinity, then we can say that the test is inconclusive. For this note over here, we're just saying this, we're kind of taking care of that statement right here as long as a sub n is greater than 0 with this absolute value symbol. So that's the thought process behind the ratio test. So I want to do a few examples, and hopefully that'll give you a good sense of how this test works. So let's start with this one. We're going to, number 7 here. We're going to look at using the ratio test to see if this series converges, diverges, or if we can just say that the test is inconclusive. So let's look at the limit of this particular series, or the ratio of this series. So I'm going to rewrite this as such. I'm going to say, all right, let's look at the limit as n approaches infinity of the absolute value of this ratio. So we're going to take 1 over n plus 1 factorial, 1 over n plus 1 factorial. And I'm going to divide this by a sub n, or I'm going to divide this by a sub n here. Well, again, when you're dividing by a fraction, it's the same as multiplying by the reciprocal. So I'm just going to write this as times n factorial over 1. Now, just like we did before in the previous example, let's clean this up a little bit. Well, n plus 1 factorial is equivalent to, and you don't always have to write this out, I'm just doing this to model it, n plus 1 times n factorial, times n factorial. That means I can divide this n factorial with this n factorial up here in the numerator. So what that allows us to is rewrite this as the limit as n approaches infinity, and our ratio would then just be 1 over n plus 1. Absolute value of 1 over n plus 1. Now, what do we know about this limit? As n gets closer and closer to infinity, this ratio is going to get closer and closer to 0. And since this limit of this ratio between terms is less than 1, we can say that this series converges by the ratio test, RT for short. And as I'll often say, I'm okay in my class with you writing RT as you're doing your work. For things like exams or the AP exam, you want to make sure that your reader knows exactly what you're referring to. They may not be familiar with RT. So you want to say something like ratio test or write it out there. In general, if you're wondering whether or not you should write something out fully, write it out fully. If you have to ask yourself that question, then you already know the answer. Write it out to be safe. So let's try number 8 now. So again, we're going to look at the ratio between terms here. So we're going to write this as the limit as n approaches infinity. And in fact, let me actually move this up here because I have a feeling we're going to need a little bit of space. So the limit as n approaches infinity of the absolute value of the ratio of 3 to the n plus 1 power. So I'm writing out my next term, 3 to the n plus 1 power over n plus 1. If I divide it by a sub n, which means I'm going to divide it or multiply it by the reciprocal, that's n over 3 to the n. Let's close that absolute value. So now let's think about this. Is there anything that I can clean up here? Well, using some of the power properties here, we can say that 3 to the n plus 1 divided by 3 to the n, well, that's just equivalent to just a 3, right? We can just, again, 3 to the n plus 1 over 3 to the n would just be equal to 3. Well, since that's a constant, I can just move that 3 over to the outside of this limit, right? Us taking the limit as n approaches infinity will not impact that 3 in any way. So I'm just going to rewrite that as 3 times the limit as n approaches infinity of the absolute value of n over n plus 1. And for those of you who are curious about the absolute value here, I know that since my lower index is 1, I don't really have to worry about the absolute value. All of my n terms here are going to be positive. So if we disregarded the absolute value here, we'd be fine. But again, to be safe, leave that in there. Well, what do we know about this? What is the limit as n approaches infinity? Well, the numerator and denominator have the same degree. So that limit of all of this is going to be equal to 1. But since we have that constant 3 on the outside, we can then say that this is equal to 3. Well, let me actually write it out here because I'm going to need some space to write out whether or not this converges. This is equal to 3. So the limit of the ratio between consecutive terms here in this case, this time, is greater than 1. So just intuitively think about what that means. If the ratio between terms is greater than 1, that means these terms are getting larger. Therefore, we can say that this series indeed diverges by the ratio test. Okay? All right, let's just do one more together now. Let's try something like number 9. So number 9 here, we're going to again write the limit. We're going to say the limit as n approaches infinity of the absolute value of 1 over root, and be careful here with your grouping. I'm going to evaluate this a sub n for n plus 1 to find a sub n plus 1. So that's 2 times n plus 1 divided by a sub n, or times a reciprocal. That's root 2n over 1. So we can then rewrite this as the limit as n approaches infinity of the absolute value. Now, we're really just concerned with this term in the denominator, right? So we notice that there is a root 2 in both the numerator and denominator, so we can just divide those out. And what we're left with is root n over root n plus 1. Now, in this case here, what is the limit as n approaches infinity? Again, Same degree in the numerator and denominator. This time, this is equal to 1. This limit is equal to 1. Therefore, our ratio test actually doesn't help here. It's inconclusive. Well, actually, I shouldn't say it doesn't help. We can at least rule this out here. It's inconclusive by the ratio test, meaning we have to use some other test. And we'll be using or learning quite a few in this chapter. So stay tuned. We will have some way of being able to find whether or not this series converges soon. So go ahead and try the next three on your own and check your answers with the solutions I've posted. And hopefully that gives you a good sense now of how the ratio test works.